I'm DJ the Deconstructor, and you have just entered the Deconstruction Zone. Before we jump into today's video, be sure to like, share, subscribe, and hit the notification bell to be updated as new content arrives. Doing so helps this channel grow. Today, we're doing a science. We're deconstructing dimensional analysis. We will break down dimensional analysis into small, bite-sized pieces. Understanding dimensional analysis is useful in chemistry and physics, and it happens to be one of those things that's useful in everyday life and not only science. What is dimensional analysis? Besides being lofty-sounding, it's a way of performing calculations with measurements. Physics, chemistry, and many other things in life have measurements associated with them. If you've been to the gasoline store lately to buy your car food, you may have ended up complaining about the price of gasoline per gallon or the price per liter. If you're talking to your friends about the weather, you talk about the temperature measured in degrees Celsius, Fahrenheit. If it rains, you might talk about how many inches or centimeters of rain fell. Things having measurements often need to be converted from one measurement to another. We may want to convert Fahrenheit to Celsius, or gallons to liters, or pounds to kilograms. Sometimes, instead of converting between measurements, we might combine them to mean something new. We may want to talk about energy consumed in a period of time and express our values in terms of joule seconds. There are limitless applications. Let's take a look at how the rules of dimensional analysis help us convert units. We will start by using dimensional analysis to solve an everyday problem. Pretend that you've just taken a new job and you're being paid an hourly rate of $15 per hour. You want to create a budget. This means you want to know how much you will make in a day, a week, a month, and a year. You can probably do this without using dimensional analysis, but we will set this up and see what it looks like done the dimensional analysis way. The first thing you will need is a map. If you're new at performing dimensional analysis, creating a map is a crucial step. The map will provide a guide for setting up our conversion steps. There's usually more than one way to get from point A to point B. It's important to think through how to get from the starting point to the ending point. If you were mapping how to get from New York to Los Angeles, there are a lot of roads you might take, but does it really matter what roads you take on your trip? Not really. The same is true with dimensional analysis. You can choose a number of different ways to get to your goal. It just has to make sense. That's why we make a map and follow the map. In this new job, you're being paid $15 per hour, and you want to know how much that is per day, per week, per month, per year. Let's map it. Notice where I start with my map. I began with hourly rate. That's because that's what I already know. This is very important. Always identify what you know and make that your starting point. Next, I will convert my value to a daily rate, a weekly rate, a monthly rate, and a yearly rate. Now that I have my map, I want to mathematically describe the relationship of each point on my map as it relates to the previous point. My starting point is hourly rate $15 per hour. I'm going to write it mathematically as $15 over 1 hour. Notice what else I've done here. I've written out my units. 15 is described by the unit we call dollars. Without the unit, 15 is meaningless. Walk up to anyone and say, "I have 15. The person is likely to say, 15 what? Cats? Dogs? Monkeys? The units provide meaning to the numbers. Without the units, numbers are just numbers and have about as much meaning as selecting a novel from a shelf, then opening the book and selecting a single word at random. My next stop on my map is daily rate. I will express it as dollars over 1 day. We move from daily rate to weekly rate, and I write it as dollars over 1 week. And we have monthly rate. That's dollars over 1 month. And finally, yearly rate, dollars over 1 year. We're now ready to determine our conversion factors. I want to refer back to my map, and I've written down my mathematical forms in the same map order. We need to think about the conversion units. How, for instance, am I getting from dollars per hour to dollars per day? We have to know how many hours there are in 1 day. If you say there are 24 hours in 1 day, well, you're right, but you're also wrong. That's because we're not just talking about an ordinary day. We are talking about a work day. My employer is not going to pay me for surfing the internet, pushing food into my nutrition hole, or sleeping. My boss expects me to work for 8 full hours. That's what I'm being paid for. 1 work day equals 8 hours. That's what I'm putting down, 8 hours per 1 work day. As I move to weekly rate, I'm defining that as 5 work days per 1 work week. Notice I did not define it in terms of hours, but rather in terms of days. When defining your conversion factors, try to set them up so as each new conversion factor is defined, it relates to the previous conversion factor and not back to the very beginning. It looks like we have a problem when defining the conversion for monthly rate. Take a look at the calendar for July 2022. Notice that there are 4 full weeks in July, but the 1st and the 2nd of the month and the 31st of the month are in partial weeks. The number of weeks in the month are not consistent from month to month, and the number of days in the month are not consistent. It will be better if we do not convert directly from weeks to month or from day to month. It will be better to rearrange our map to go from weekly rate to yearly rate and then to a monthly rate. Our new map looks like $15 over 1 hour, 8 hours over 1 work day, 5 work days over 1 work week, 50 weeks over 1 year. You might be saying, hey, deconstructor, hold on, you made a mistake. There's 52 weeks in a year. You would be right, and you would be wrong. There's 52 weeks in a year, but your employer gives you 2 weeks vacation every year. That means we have 50 work weeks in 1 work year. Now, I chose this example to point something out. Don't make the assumption that we put every fraction together so that each fraction is something over 1. The first few fractions just worked out that way. Also, the last fraction has a 1 on top. That is not a rule either. But there is a rule. Look at the first 2 fractions. We have $15 over 1 hour and 8 hours over 1 work day. Our first fraction has dollars on top and hours on the bottom. Our next fraction is arranged so that it alternates matching units between top and bottom. Our conversion factor, the second fraction, contains hours and work days. The fraction it's bumping up against doesn't have work days, but it does have hours. We do not rearrange the first fraction. That means we have to arrange the second fraction so that hours is on top. What we were doing, I call fence hopping. The fraction line is our fence, and we continually hop units from one side of the fence to the other. Here is why. If we treat the units like they are variables in algebra, they can be canceled out. Hours are on opposite sides of the fence, they will cancel. Work days are on opposite sides, they will cancel. Work weeks are on opposite sides, they cancel. And yes, work years are on opposite sides, they will cancel. Let's look at only the first two fractions. After canceling hours, we're left with uncanceled units, dollars, and work day. Let's pull out our calculator and do the math using just these first two fractions. We will multiply everything on top and everything on bottom, then divide the two numbers. We have 15 times $8 divided by 1 times 1 work days to equal $120 per work day. Let's look at the first three fractions. We have $15 over 1 hour, 8 hours over 1 work day, 5 work days over 1 work week. We know hours cancel, but look, work days cancel too. That leaves us with dollars per work week. Let's do the math. 15 times 8 times $5 over 1 times 1 times 1 work weeks to equal $600 per work week. Working through the first four fractions, we have $15 over 1 hour, 8 hours over 1 work day, 5 work days over 1 week, 50 weeks over 1 year, and after canceling our units, we're left with 15 times 8 times 5 times $50 divided by 1 times 1 times 1 times 1 work years to equal $30,000 per work year. And finally, we'll do the math for the entire set of conversions. $15 over 1 hour, 8 hours over 1 work day, 5 work days over 1 work week, 50 weeks over 1 work year, and 1 work year over 12 months. We will cancel our units. And we are left with 15 times 8 times 5 times 50 times $1 over 1 times 1 times 1 times 1 times 12 months equals $2,500 per month. Now let's do something a little more sciencey. Let's work a physics problem. Imagine there is a single oxygen molecule in a container. We happen to know that the molecule is moving at 500 meters per second. We want to know how fast this particle is moving in miles per hour. The first thing we do is set up our map. We want to start with what we know, meters per second, and end with miles per hour. Our map looks like this. We go from meters per second to kilometers per second to miles per second. That takes care of converting our distance units. We will now convert our time units. We will change miles per second to miles per minute to miles per hour. Here are the conversion factors we use. There are 1,000 meters in 1 kilometer. 1 mile is 1.069 kilometers. 1 minute has 60 seconds, and 1 hour has 60 minutes. Our dimensional analysis problem is set up like this. 500 meters over 1 second. 1 kilometer over 1,000 meters. 1 mile over 1.069 kilometers. 60 seconds over 1 minute. 60 minutes over 1 hour. Before we punch any buttons on a calculator, we want to see if our units cancel to leave us with what we want to know. Meters cancel. Kilometers cancel. Seconds cancel. And finally, minutes cancel. We're left with miles per hour, exactly what we're after. This is what we will put into our calculators. 500 times 1 times 1 times 60 times 60 miles over 1 times 1000 times 1.069 times 1 times 1 hours to equal 1,683.816651 miles per hour. Note, if you're doing this in class, your instructor will probably require that your answers be reported according to the rules for significant digits, which means in this case, we will report our number as 1,684 miles per hour. Let's do one final problem, something chemistry related, a stoichiometry example. We have 63 grams of glucose, that's C6H12O6. How many grams of carbon are present in that 63 gram sample? We'll look at stoichiometry in depth in future episodes. For now, just know that stoichiometry maps tend to look like grams converted to moles, to a mole ratio, to moles back to grams. We have to work in terms of a unit of measure you may be unfamiliar with, the mole. A mole is 6.022 times 10 to the 23rd of anything. It could be atoms, it could be molecules. Referring to the periodic table, carbon has 12 AMU. That's 12 grams per 1 mole of carbon. Also, using the periodic table, I can calculate there are 180 grams in 1 mole of glucose. My map looks like this: grams glucose to moles glucose to moles carbon per 1 mole of glucose to grams carbon per 1 mole of carbon. I start with 63 grams of glucose and put that over 1. I have no units on the bottom of this fraction. Next, using the periodic table, I determined that the molecular mass of glucose is 180 grams. This is what I put in my second fraction, 1 mole of glucose over 180 grams of glucose. My third fraction is my mole ratio. The formula for glucose starts with C6. That tells me there are 6 moles of carbon in 1 mole of glucose. I put 6 moles of carbon over 1 mole of glucose. Finally, I learned from the periodic table that there are 12 grams of carbon in 1 mole of carbon. Notice GC6H12O6 grams glucose on the top of my first fraction cancels with grams glucose on the bottom of the second fraction. Moles glucose on the top of the second fraction cancels with moles glucose on the bottom of the third fraction. And finally, moles carbon on the top of the third fraction cancels with moles carbon on the bottom of the fourth. This leaves only grams carbon, which is what we were after. The math looks like 63 times 1 times 6 times 12 grams carbon divided by 1 times 180 times 1 times 1 to equal 2.4 grams carbon. Following the rules of significant figures, that rounds to 2 grams of carbon. Let's summarize what we've done today. There are some basic rules we've been following. First, identify your starting and ending points. Then, map how you want to proceed from start to end. List your conversion factors. Always convert in terms of the preceding uncanceled unit. Alternate your units so they cancel out. Check your canceled units to make sure that you're ending with the units you are looking for. And finally, your answer will be the product of the terms on top divided by the product of the terms on the bottom. I hope this helps with dimensional analysis problems. By the way, this is Sunshine. Sunshine wants you to like and subscribe and turn on the notification bell so you can access new content as it's released. If you don't like, subscribe, and hit the notification bell, Sunshine will know, and she'll come to your house and she will deconstruct something. Until next time, this is DJ the Deconstructor wishing you happy sciencing.